Welcome to the last thermodynamics video. Congratulations on making it this far and not ripping out your eyes and ears from watching too many videos. But we've made it. We're at the last one. And what we're going to do in this video is go through this kind of sheet or template that I've made up and try to make hopefully what will be a useful study guide and equation sheet that you can bring with you to the exam. So we'll go through this and kind of highlight some of the key points, the key things that, like assumptions and cases that we have and we've used throughout the class. So if you don't have this sheet, it's on Moodle. Pause the video, go and print it off, and then come back and join us here in a second. Right, if you have your sheet, I'm going to just fill this out and talk about things as I go, and you can follow along and fill out and take notes to make sure that you remember when we can use which different equations. We have two different equations for ideal gases and real gases. PV equals RT and PV equals ZRT. Just a couple notes, right? R is gas dependent. Z is found in, or is found, I guess not in, but using the chart where we find like the reduced temperature T over the critical temperature and the reduced pressure P over the critical pressure. There are a lot of similarities for energy balances for control masses and control volumes. For control masses, we have delta U equals Q12 minus W. For a control volume, our general energy balance is plus delta EK plus delta potential energy equals Q minus W. I'm writing these both in the specific variables, but we can multiply by mass or by mass flow rate to get kind of a different, like capital letters or capital letters with a dot. Work for both is similar, but a little bit different. For a control mass, work equals the integral of P dV. For a control volume, it's a little bit different because the flow work is already taken into account in enthalpy. So this is, minus V dP. Heat is the same. Q12 equals the integral of T ds, and Q equals the integral of T ds. Okay, so those are equations governing heat, work, and our general energy balances. We're often going to be calculating thermal energy changes, enthalpy, or internal energy. Delta U equals CV, delta T, and delta H equals CP, delta T. So both of these are assuming constant heat capacity. So both of these are assuming constant heat capacity, and ideal gas, solid, liquid behavior. So they're both kind of assuming ideal behavior, which is fine because that's what we happen to be dealing with, at least in this class. The two different heat capacities, CV and CP, there are some useful relationships that we should just remember and write down. We have CP equals CV plus R. This is for an ideal gas. And Cp equals Cv for ideal solid / liquid. Right, and by ideal solid liquid, we mean if I can spell, incompressible. The last relationship or equation that relating to heat capacity that we should make sure we know is that K equals the ratio of the heat capacities. We can look that up in our table, but just so that we remember that K is the ratio of the heat capacities. There are a few different ways that we can calculate entropy. So we'll write down a few equations here. Delta S equals Cp times the natural log of T2 over T1 minus R times the natural log of P2 over P1. And delta S equals Cv times the natural log of T2 over T1 plus R times the natural log of V2 over V1. So for these guys, both work for ideal gases with constant heat capacity. So if Cp and Cv are constant, these work, and if we have ideal gases. When we have that, we can choose either one. They're the same thing, just two different forms of it. So we choose whichever one. If we know temperature and pressure, we choose the top one. If we know temperature and volume, we choose the bottom one. A note on this, use Kelvin. When we're dealing with entropy, we have to be using Kelvin. The last equation for entropy is for solids and liquids. That is delta S equals Cv times the natural log of T2 over T1. So this is for ideal solid and liquid. Again, ideal meaning incompressible. Also for that, we're going to be using Kelvin. There are a couple useful equations relating temperature, pressure, and volume for ideal expansions or compressions. Ideal, that means delta S equals 0. So this is adiabatic and reversible. So if we have something adiabatic and reversible, there are a couple useful equations. We have T2 over T1 equals P2 over P1 to the K minus 1. I'll write that a little bit better so that you can tell it's in the exponent, K minus 1 over K. Or we have T2 over T1 equals V1 over V2 to the K minus 1, or our last equation, P2 over P1 equals V1 over V2 to the K power. Right, this last one means that V to the K is constant. And then the last notes that we'll have, right, use the easiest. What I mean by that, if you know temperature and pressure, use the temperature pressure one. If you know pressure and volume, use the pressure volume one. They're all the same equation. They all work for ideal expansions and compressions, delta S equals 0. We changed from one to the other with ideal gas law. So these all are for ideal gas constant heat capacity. And again, the same warning as the one above. For these ones, you have to use Kelvin. So maybe I'll write it over here. Use Kelvin. Use Kelvin. There are a couple different equations that we can have for work, for determining work. So we have for a general polytropic process, right? That's one where P V to the N is constant. Then our equation for work 1, 2, equals P2 V2 minus P1 V1 over 1 minus N. It's our general equation. For P2 V2 minus P1 V1 all over 1 minus K. This is for an adiabatic. Reversible process, delta S equals 0, right, which is PV to the K is a constant. Right, we just said that up above a little bit. So these are two similar equations. The cool thing to note is, right, these are both equations for ideal gases. The last kind of interesting equation, the interesting special case, is for an isothermal process. For an isothermal process, we have a couple of equations. Work equals RT times the natural log of V2 over V1. I think I only wrote one of these in class, but they're all equivalent. Equals RT times the natural log of P1 over P2, which equals P1 V1 times the natural log of P1 over P2. So these are all for isothermal. And I'll just make a note, all ideal gas, my note's getting a little ugly, let me erase it. all ideal gas constant heat capacity. So all three of those equations, all three sets of equations are for ideal gas constant heat capacity, and then for specific processes, whether we have a polytropic process, an adiabatic reversible process, or an isothermal process. Really, all of those are different ways to solve this general equation up here at the top for a control mass. So all of those are specific solutions of that along these specific paths, these specific pathways. That's isothermal reversible, a general polytropic process. This is, yeah, that as well. A general reversible polytropic process. So all of these for reversible processes. So that's kind of the summary. It is a lot of equations. Hopefully, looking at them in this way helps us keep some of these straight. I've kind of just written the simplified versions that we've used, that we'll use the most. So for example, like for delta U and delta H, just wrote CV delta T, CP delta T, rather than the integral form and the simplified form. So I've tried to keep it as general as possible. Hopefully this gives you a good start as you're making your note sheet for the final exam. Congratulations for making it this far in thermo. You're almost there. Let's get ready for the final exam.